Cool. So since my title has generative AI and vector databases, I thought I'll start with the easy part. I just asked ChatGPT to explain generative AI to me. It actually did a pretty decent job. And I think that covers all about generative AI that I want to talk about. I'm kidding. I do want to summarize a little bit. I think you've heard about generative AI a lot over the last couple of days. I'm not going to say anything fundamentally new here, but I want to maybe present a little bit of how I think about this journey, which is relevant to why vector databases are even relevant. So to summarize, I want one takeaway from this talk to be, what is a vector database, right? If you go away from this talk with that understanding, that's great. The second piece of understanding is, why is it even relevant to generative AI? Okay, that's basically it. Now for that, I need to look at the history of NLP a little bit. So we started with fully supervised training with handcrafted features, which required a lot of domain expertise, also required a lot of machine learning expertise. And over time, we've moved away from domain expertise, first into neural networks that actually could co-learn features, but secondly into language models that could be fine-tuned. But finally, we are at a stage where you can use large language models that don't need fine-tuning. Okay? So I'm going to be specifically talking about this latter part of models, right? And what is really exciting about that is it has democratized machine learning, right? Because you no longer need domain expertise and you don't need machine learning expertise to start leveraging this, right? What large language models have also done is they've allowed you to use a technique called prompting in order to be able to tell it what task you want it to do and provide it enough context to be able to do that task. Okay? So the workflow today, or these days, for generative AI looks roughly like this. Okay? You start with the user prompt, you have some sort of an orchestration layer that could even be an agent, or you could have nothing. You could just go into ChatGPT and just type, right? At that point, you've bypassed all of this. And what an LLM does for you is, based on the chat prompt and based on the chat history, it tries to do the task that you're asking it to do. Okay? This is already pretty phenomenal, right? There is a lot of things that it can do today, even with this sort of a basic workflow, but it has some problems. The problems that it has have to do with a few categories. First of all, it's architectural limitations. So because this is a large language model that is trained, it is only as good as the training data that went into it, in some sense, and in some sense, its knowledge is frozen as of the training. And training is expensive. Training a large language model is very expensive, and retraining it is also expensive, which means it's very costly for you to keep up with evolving knowledge. So in some sense, freshness is highly expensive. The only other way that the large language model actually interacts with the rest of the world is through the context that you provided. So that's the other source of information for it. Now, that context window is finite, and it's limited in terms of memory from what it can do there. Now, there have been attempts to increase that context window, so make the context window really large. That actually doesn't help. So it leads to another problem called hallucinations, which I think Ofer talked about this in the morning, so I won't necessarily be spending time on it. But basically, the second problem that large language models have is they either don't have the knowledge, or they think they know what you're asking them to do. Either way, they confidently respond, right? And that's what we call hallucination. The hallucination actually gets worse with large context windows. So if you think that, okay, instead of having 4,096 tokens, the number of tokens is much larger, maybe I can stuff more context into it, maybe the LLM will do better, it actually does worse. Okay? The other part is, of course, when you start doing something serious with LLMs, it's important to actually attribute content. And attribution of content is really hard today with the workflows that I just described. The last part is actually privacy. So sometimes you want only certain people to be able to see your content. Sometimes you want to control how that content is even surfaced to an LLM and made available to other people, right? And the ability to actually retract content. So there is some content that you might have previously surfaced that you want to now retract. Okay? All of these are actually fundamental challenges to LLMs today. Okay? Oh, can you all hear me? Okay. Cool. So I'm going to describe a workflow that actually has a potential of solving a lot of these problems, or at least making dramatic headway into solving these problems. I want to illustrate with an example. This is a real example that I'm using here. So on the top, I'm using ChatGPT 3.5. I just typed what Pinecone pod type should I use for high throughput. Okay. Of course, if you type in what pod type should I use for high throughput, the results are even worse. Okay, because clearly ChatGPT doesn't understand what Pinecone is, right? But here, it is actually giving me back a result, but it's giving me back a result that doesn't make a whole lot of sense. Okay, but it sounds plausible though, right? It's very plausible that there is a large pod type in Pinecone, which actually there isn't, right? It's very plausible that the rest of the sentences are somewhere in the documentation in Pinecone, which they aren't. Okay. However, what would you like it to return? What you would like it to return is something that I've highlighted in the blue here, which is this is actually part of the documentation. So what's below is part of the documentation, but it's not the exact documentation. In some sense, it's a summary of the documentation. It is actually very relevant. This is exactly what I was looking for. Okay. In fact, I would have gotten the same result without even typing the keyword Pinecone. Okay. What you see here in one shot is it's providing you attribution, which is it's telling you exactly what source this thing came from. It's providing you privacy in the sense that this is only available when that context is available to this workflow. It is incorporating knowledge, right? But it still has privacy. So this is what we really want. Okay? How do we get there? The way we get there is through a workflow like this. Now again, Ofer covered this in the morning, so I won't go too deep into everything you can do with this workflow. But roughly what you want is you don't want to send user prompts and context directly to something like ChatGPT or an LLM. What you want to do is, and again, you don't want to stuff all your documents into the context because again, there's a lot of noise with that. What you want to do is to have a workflow that takes your documents, chunks them, sends them to a vector database. And we'll get into a moment why you need a vector database here. But just for a moment, assume it's send it to some semantic search layer. That semantic search layer basically is responsible for doing the following, which is when you get a prompt, it's going to find the most relevant chunks of data to your prompt, going to pass it in the context window. So that becomes part of your chat history and essentially instructions to ChatGPT, and is the knowledge base on which it's operating. Okay? And then the LLM's job becomes to now perform the task you want with this additional set of facts. It could even be summarizing those facts. Okay? Make sense so far? Cool. So I want to take a moment to actually, going back, I slipped in a vector database here, right? The rest of the talk is going to be about why do you need such a thing. Okay? First of all, it's clear that when you have a query prompt or any sort of a query that you want to retrieve information from, you kind of want a retrieval engine on the right-hand side. You want something that's able to do retrieval. Vector databases are that thing that allow you to do retrieval. Okay? Now, retrieval can be done using multiple techniques. There is so-called dense retrieval, there is so-called sparse retrieval, there is so-called hybrid retrieval. Retrieval engines have existed for decades. Elastic is an example of a retrieval engine. Any sort of text search engine is kind of doing retrieval. But at the end of the day, they're all some form of vectors sitting somewhere. Okay? And I want to dig into that a little bit. So the workflow really looks like take your text, chunk it, use an embedding model. So from the chunks and the embedding model, you get a vector. Now this vector could be an array, basically thought of as an array of floats. Okay? Or it could also be thought of as a dictionary. The difference being that the array of floats is a more natural representation for what's called dense vectors. Dictionaries are more natural representation for sparse vectors. But either way, it's really a vector. Okay? And you take those vectors and you put them in some store. What you want to do in order to enable retrieval augmented generation or RAG is when a query comes in, you kind of go through the same workflow. From the query, you get to a vector. And what you want to do is to look for the closest vectors in your corpus. Okay? The idea being the semantic relationship between a query vector and chunks of documents in your corpus is represented and captured by performing nearest neighbors on this database. Okay? So searching for the nearest neighbors in this sort of a system tells you something about the semantic relationship between the query and the chunk of document. Make sense so far? Now, so far so good. So basically what we are doing is we have an array of floats. There is an entire corpus of an array of floats. We get a new array of float and we want to know what are the closest vectors to this particular vector, right? That is it, okay? Why can't your database do this today? Why can't, say, Postgres do this today, right? The problem is there is a lot of techniques over decades for database indexes and efficient retrieval of data from a database. Practically all of it breaks down once you get to high dimensions. So anything that you do that's not aware of geometry starts breaking down at relatively low dimensions. So for example, breaking up space recursively, which is a technique that's very commonly used in databases, does extremely poorly once you get to high dimension, right? What happens in this example is once you go to 768 dimensions, you have to look at pretty much the entire corpus to be able to retrieve the nearest neighbor, okay? So you're no longer able to take advantage of any sort of indexing to do this right, okay? So any sort of exact search or any sort of traditional indexing fails. The other problem that you have is when you're looking at vectors and when you're searching through vectors, you're interested in asking types of questions that you've not been asking from traditional data. For example, you're looking at a new type of filter where you say, I have a query point, give me everything within a threshold of this query point. So that's what I've called here as a ball filter. You might be interested in what's called a half space filter, which is give me everything that has an inner product that's larger than some number. Now, the one on the left-hand side, the half space filter, is very commonly used for information retrieval with text, okay? So things like, for example, maximum inner product search is something like that. So now you have these operations you want to do on this sort of data that is so specific to geometry and so specific to the understanding of geometry that if you don't understand geometry, if your database doesn't understand geometry, it can't do this efficiently, okay? Okay, so maybe there is another approach we can take here, right? There is a bunch of libraries that exist today, whether it is hashing-based, compression-based, whether it is HNSW, whether it's FICE, and so on. These are really good libraries that do vector search. So if you give it a set of vectors, it's going to do the job that I just told you of being able to fetch the top K and so on. Why can't you just use it, kind of take it as your vector index, so to speak, bolt on a database on top of it for storing your actual data, and then be done with it, right? Why do you need a new type of database for this? The problem here is now you have the other problem. The moment you do that, you now have a system that really understands geometry well, okay, but it doesn't understand data management well. Okay? An example of that is, imagine you have a small filter where you say, I'm not interested in all documents that are close to a particular query vector. I'm only interested in documents that maybe are available in a certain region, or maybe have some other filter that I care about, right? In any sort of a traditional vector index, this filter is going to be contrary to the vector index filter itself. So in other words, applying this filter is going to negate the vector index to begin with. So you're back to searching over the entire database. Okay? I'll give you an example here. So I'm going to pick an example that's really simple to kind of understand what's happening. This is good for forming intuition. It's not how actual vector databases work, right? So just use it for intuition, but it's not, it'll give you intuition, but it's the actual code or the actual system will look very different. So here, a typical workflow of a graph-based index for vector search would look something like this. In a pre-processing phase, you build a neighborhood graph. So the basic idea is that you have these vectors. You want to be able to traverse through this set of vectors when a query comes and find the most relevant one. And how do you do that? You need to have connections between them in a graph-based index. And the connections are formed during pre-processing, and you're building a neighborhood graph at that time. When a query comes in, you start at a random point, and then you just do greedy traversal. So greedily, at all points of time, you're trying to get closer to the query point. Once you get closest to the query point, you expand the search from there outward, try to find the top K neighbors. That's basically the idea around graph indexes. Okay? It's the same algorithm that's used by HNSW, which is the leading graph indexing library. The only difference is it does this in stages. So you can think of it as levels. where you're getting increasingly fine-grained, down you go in levels. But the idea is the same. So for example, when a query comes in, you start searching with some entry point at the top level. In the top level, you're moving across wider regions of space. Once you keep going to the bottom levels, you're going to narrower regions of space. That's really the idea. Okay. So in this context, I can easily explain to you why filters are problematic. Right? Imagine that there is some filter that is only allowing for relevant documents in the region that I've highlighted. Okay? So meaning all the relevant documents are there, even though the closest documents are somewhere else. So imagine that a greedy search starts somewhere. It's going to go all the way and do all the work to get close to the query point. Then it's going to expand all the way backward to get to the relevant data. So this actually spends at least 2x, maybe if not more, time than exact search. So this is actually twice as worse as brute force, right? And this is not a theoretical example. Many cases this actually happens in practice. This is a really hard problem to solve, which means that vector indexes have fundamental issues with traditional data management. Okay? They have other types of issues with traditional data management as well. So all of the indexing libraries that you have today, and for a good reason, all of these libraries either require you to rebuild your entire index, or if it's an incremental index, it's very slow to index. And it's slower to index the more data it has already seen. Okay? Which means all of the existing libraries actually force you to make a trade-off between freshness and cost. If you want to be cost effective, you really have to give up freshness. If you want to be highly fresh, you have to be expensive, right? They all have challenges with concurrent workloads. It's really hard to build concurrent indexes that are very efficient. Okay? They're all expensive. In one way or the other, they essentially have to, so if you think about data under management, imagine that I have a terabyte of data under management. Ideally, you would want, and every database does this for you, that you can store terabytes of data, but you're not paying the compute cost for terabytes of data. You probably pay storage cost for terabytes of data. In vector indexes today, you pay the compute cost for terabytes of data, even if you're not querying all the terabytes of data. Meaning, even if you're querying only a small subset of the data, you're paying the compute cost for all the data. Okay? And this is a fundamental problem. Whichever way you slice it, this is like a very fundamental problem. Okay? And they're all hard to scale. Like you can take libraries, you can bolt them onto databases and so on, but fundamentally you're limited by scale. And the only effective mechanism for scaling at that point is simply having more of these and scatter gathering, right? And scatter gather, as you all know, introduces tail latencies in queries will become P50 latencies in queries very soon. Okay. Cool. So far I summarized, what is retrieval augmented generation? Why does it need a vector database, right? Meaning, why can't you just use traditional indexes? Why can't you just take really successful and great vector search libraries and just have somehow a way to build a vector database without actually building one? Neither of those work, but what are the properties of a vector database? There are really three major properties. We just talked about it. One, it has to be geometry aware. So for you to not have to pay the cost of, essentially pay the compute cost proportional to data under management, it needs to be able to avoid vast swaths of data that it never needs to look at. And it can only do that by effectively understanding geometry really well. Okay? It also has to provide this, so it's not enough to understand geometry well, it has to understand filters really well, meaning your indexes have to work together with filters. Okay? If they don't, meaning it has to, in some sense, understand traditional database indexes just as well as it understands this new type of index. Okay? The indexes have to be adaptive, meaning you can't force a system, you can't force people to choose a system where they have to pay extremely high cost for freshness even if they don't need it, or to forego on freshness even if they need it. So either way, it's a very bad choice to make. So the only successful vector databases here will be the ones that are actually adaptive. And by adaptive, I mean, can they respond fast to updates, deletes, and so on? So let's say you added a new document how fast is it available for search. Let's say you've removed a document because you didn't want it to be available in the knowledge base. How soon after removal is it actually removed, right, from search? Things like that. The final thing that's really crucial is there is a fundamental difference between vector databases and traditional databases. Going back to the very first point that I was trying to make here, exact search over large corpuses are simply computationally infeasible. Also, it's not even clear that you need that, because at the end of the day, these relevant documents are getting fed into some pipeline that's sent to a machine learning system for you to summarize or retrieve some content and so on. So at the end of the day, what matters is not the exact top K that you retrieve. What matters is the quality of your search result. Because of that, it's not even necessary that you need to be exact in this computation. So A, you don't have to be exact in this computation, and B, it's hard for you to be exact in this computation at scale. That's a fundamental property. Now, this is a very interesting property of vector databases that's not a property of traditional databases. Okay? The best-in-class vector databases will actually exploit this property, right? How do you exploit this property? You can actually make this a control trade-off, which is you want users to be able to control the trade-off between cost and recall, because at the end of the day, it comes down to it. At the end of the day, you can always do exact search over your entire corpus if it really matters to you that you have that particular recall, right? You want to maximize the recall. If you're willing to live with a recall that's less than 0.9 or some other relevance metric that you care about, you should be able to pay less, meaning you should be able to control the trade-off between cost and recall. I would say that these are the three fundamental properties that any vector database needs to kind of aim for. Now, this is hard. This requires hard work. This is a fundamentally new type of system that needs to be built. But hopefully, the point of my talk is to convince you that this is actually needed, and innovation into these areas actually have to happen. It is not something that comes for free. It's not something that has existed. None of these three things have existed in traditional databases. Adaptive indexes do exist, but they exist for traditional search patterns. They don't exist for the new type of search pattern that we need to do here. Now, of course, databases have gone in the direction of allowing you to control trade-offs. Cloud databases do this really well today, but they don't allow you to control for recall versus cost, because again, they don't understand the nature of the problem. To understand the nature of the problem, your database has to understand vectors, understand geometry, and all this better. So I'm going to pause here. I'll just have one slide on Pinecone. I wanted to talk to be more about the nature of the problem and why we are doing what we are doing. But the goal of Pinecone is to be that platform. Basically, it's self-serve platform for vector search. From day one, it was fresh to, we focused on freshness and recall, which means if you have to offer you any trade-off at all, we'd rather the trade-off be that it's a little bit more expensive in some sense, without having you to think about recall, to think about freshness and any of this. So it should be seamless to use and so on. So we've kind of erred on the side of those two areas. Of course, we are doing a lot of work on providing the best of all three, but that's fundamentally hard work. In terms of one other thing that I wanted to highlight is the difference between vector search libraries and a vector search database or vector database is that hopefully you don't have to do any tuning at all. You simply use the system. It does best effort retrieval for you. You never have to think about it twice. Okay, and that should be one of the fundamental goals as well. So I'm going to pause here. I think I have about 5 minutes, so I'm going to pause and ask if I have any questions. Yes.
So on the slides, you showed that there's a big database of it and semantic search. So
yeah.
Pinecone offers for semantic search?
That's a great question. So semantic search is basically a layer that sits above any sort of vector database. In Pinecone, we have this, I talked a little bit about sparse and dense retrieval. So Pinecone offers something called hybrid retrieval, which is you can actually do sparse plus dense together. There are also these days models called like Splade, which allow you to do sparse-only indexing, right? What Pinecone does is it provides the core database that does efficient search. There are libraries we are working on that make it easy for you to take text and throw it into Pinecone. So some of it we've already released. Pinecone text is one of them. There's the demo that I showed, the example I showed you of retrieval augmented generation is a library we are working on to open source. And these are tooling that we hope will help make it easy for people who have just unstructured data and text, who don't want to think about chunking, who don't want to think about model integrations, and just want to use Pinecone. So that's also the goal. But we are kind of separating out. In my talk, I was focusing more on the kind of vector database itself, the core of what the system has to do. But then on top of that is things like ranking layers, learning to query, ease of integration with models, better chunking, and so on. So Pinecone views it as tooling that we provide as much as possible, either through documentation, open source libraries, where possible, integrate with LangChain and other agents and orchestration layers to make it easy for people to take advantage of systems like this. Any other question?
Oh, sorry. Yes,
How do you define relevancy?
That's a hard question. I mean, information retrieval has a bunch of metrics here, but at the end of the day, it's user defined. Like we look at recall and things like that because that's traditional vector search metrics. But like I said, that doesn't always translate to relevance. At the end of the day, the relevance is, in some sense, use case and human defined. Right? So your best metrics today will be from information retrieval, basically. Yeah.
Time for one more.
Yeah.
And also, I should mention, we do have office hours. It's really right behind this wall here. But if you go out to the right and the right again, there are the open talks, and then there's also the room for office hours for speakers.
Cool. Yeah.
Is there support for low-rank approximation type searches?
Yeah, you mean projection into lower dimensions, and you can do that on the client side. You can absolutely do that. So for us, it's just a vector embedding. You can absolutely do projection to a lower rank, but you are in charge of then doing it on both the query and ingestion side. So you can absolutely do that. We don't do that today. We do use projections on our side. So basically, in some sense, we have algorithms that kind of produce compressed indexes. So we don't actually take your raw vectors and use them for indexing. We use all sorts of compression and all sorts of secondary indexing and so on. What we don't do today is, and is say work in progress, is understanding your query patterns and being able to do further optimizations on your index based on that. There's a whole slew of literature and whole slew of techniques we can apply here, but I think that's still something that's an open question.